Hello to all good people of the world. This is Paul Whittakin returning to you with the universal law of numbers. And today what I'm going to be doing is giving out free textbooks, calculators, teacher, and the answer sheets too. However, before we get to all of that, I wanted to just briefly kind of review the universal law of numbers matrix, which is the 369 code. And we can just remind everyone that the 369 code is made up of individual codes such as 248751, 248751. Okay, so 248751, we're going to be pretty much looking at that at one point today, and I'll describe to you how, even though this universal law of numbers might be unfamiliar to people, it's not difficult to understand. The first thing we just have to understand is this. So, this universal law of numbers is not a creation of man. It's given to us by the universe itself. And the universe did this. It goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, we may immediately notice that 10, 11, 12 reduces back to 1, 2, 3 again, and the whole sequence starts all over. So, when we study the universal law of numbers, the 369 code, we recognize that the universe has told us that, and we don't disregard it. The reason we don't disregard it is because it's the foundation of the 369 code. It gives us the 369 code, and the 369 code is what gives us mathematics. And if we were to discard that as of lesser importance than it is in fact, then we would never understand what this universal code is, what the 369 code is, what we refer to as mathematics, what that is, because mathematics comes from the 369 code. So the 369 code, I try and point out, it's not a new thing. I mean, this is the way it looks from our perspective right now, but, in previous civilizations, for instance, the Romans would have written it something that looks more like that. Okay? But in effect, in reality, it's the same exact thing. Now, going back even further, probably to the time of Pythagoras, etc., they noticed the connection between the numbers and the geometry. So probably they did something that looks like that. But far, far, far before Pythagoras and all of his kind of people came along, in the Stone Age, whoever these cave people were, eventually they needed to do some kind of accounting for their belongings, and they used sticks. And then a clever one came up with the idea that they can make this number code by going one stick, putting 2 sticks together, 3 sticks together, 4 sticks together, 5 sticks together, 6 sticks together, 7 sticks together, 8 sticks together, and 9 sticks together. And when they did that, they understood that they got the sequence, and not only did they get the sequence going across, some wise caveman came up with the discovery that this is a repeating sequence in this direction as well, going up and down, and this is the repeating sequence, and this is the repeating sequence. And before you know it, they had people building monuments and pyramids and all kinds of majestic architectural structures, very similar ones all over the world. Who knows? Now, maybe I'm making this up, maybe I'm not, I don't know. But the fact of the matter is, the Stone Age, this goes back way before that. It's just a discovery that man, you see, many men have been very good at mathematics. Some people are very good at mathematics, but no man has ever created the mathematics. Okay? It's just discovering something that exists in nature. And I point that out now. What I will show you is here's another way we can look at the universal law of numbers, and it's the same exact thing. But the thing that we notice is, now when we start doing it like this, basically what we're doing is we're moving into what people would probably refer to as algebra, because all algebra is to me, and on with the calculus and the whole thing, is that somebody figured out that you can use, for instance, a letter like the letter X to substitute for the number, the letter X, the letter Y, the letter Z, for instance. And if one were to really be able to study the 369 code in depth, we would need basically, it's a 6-dimensional diagram. It's demonstrating to us a 6-dimensional universe and not a 3-dimensional universe at all. So in any case, this would be the 369 code, just like the one in front of it, and it goes on forever because the sequences repeat. And if we go further and further, we can even go across. See, it goes 10, 11, 12, 13, 14, 15, 16, 17, 18. But that's the 369 code as well. And if we were to reduce all of those numbers, we would come up with the same exact matrix as the 369 code, because it's only logical, because they're the same thing. Okay, so it goes across and it goes on forever, and we can keep on going and going and going. 19, 20, 21, it doesn't matter how far we go, it goes on forever. Now, the thing about this universal law of numbers, what it does is it has the capacity to teach us whatever mathematics anybody calls mathematics in its entirety. And, I don't understand that whole thing completely. This is my intuition speaking, but there are certain things about how one may approach it. Now, if one were to try to, for instance, memorize every word in a dictionary, and they open it up the first page and they tried to memorize like the first couple of words and then the second couple of words, and that would be a futile way to try and learn what all of those words are in the dictionary. So what we do is we step back, and we may ponder the situation a little bit, but we step back and we view it from the outside, and we look for these certain commonalities. And we're going to get to these commonalities because these numbers have special relationships. These are the very, very special numbers. And I just point out, in the universal law of numbers code, these would be all the perfect squares. And I would have to put one there too. I don't know how that could have been overlooked. But anyway, these are the numbers. So we're going to look just briefly at these numbers, because these numbers are the perfect squares in the 369 code. So this is the 369 code, and with the numbers, we see these particular numbers, which are the perfect squares, and if we show them algebraically in this form, then with the exponents, then that's what that diagram looks like. So it's very important to kind of get a feel for that, because all of those matrices I showed you just now, they all are essentially the same one. Now these are the way the numbers work, because we have the 2, 4, 8, 7, 5, 1 numbers, which relate to each other in a group, as do the 3, 6, 9 numbers relate amongst themselves together in a group. And when we learn algebra, and the way we're going to see it today, the reason that this all occurs the way it does is what we are needing to do is somehow transition, let's say a 369 number into a 248751 number, or vice versa, so that we can use the algebraic technique to multiply those numbers together, because those numbers, they have to have either the same exponents or they have to have the same coefficient. So they have to have the same this number, or that this number has to be the same. Otherwise, we cannot multiply them together. But as you can see, these numbers, these 248751 number sequence, they give us the 2's. And the 2's are the most prolific. And they give us the 4's. And it goes up to 256. So we can see that these common numbers reoccur over and over and over. And these are the important numbers when it comes to the 248751, and in particular to the number 64. So we're going to look at the number 64. Okay, we'll go back to the original. This is the universal law of numbers. And we need it with real numbers. Okay, I'll just take this one because they're all the same. It's just a random one. Now, in the universal law of numbers code, you see a couple of numbers that occur more than once, and in particular the number 64. So there are 54 numbers inside of here, 9 numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9. That makes 63 numbers altogether. And we have 64 occurring once, twice, and 3 times. We also have 4,096 occurring twice, and that makes them very, very special numbers. And there's another special number in here as far as that's concerned, and it's the number 729, which also occurs twice. And the number 729 is a 369 number, where 64 is a 1 number, and 4,096 is also a 1 number. 4 and 9 is 13, and 6 is 19, 1 and 9 is 1. Okay, so that was just a little ahead of itself, but what we're going to just address here is how people in the conventional world do algebra, and this terminology, these symbols, when you do it in school or whatever in the modern world, people are going to use this symbol. It's not even necessary to understand the universal law of numbers at all, but since they do it, we'll just look at this and we'll carry on. I'm just backing up for anybody who doesn't understand this thing. But anyway, if we have an x underneath the radical sign, that's the same thing as x to the half. So we have 2 squared equals 4. The square root of 4, we don't write the 2 when it's a 2. That's a 2, because 2 times 2 is 4. And when it comes to 2 to the third, 2 times 2 times 2 equals 8. Well, the third root of 8 is 2. So that's how they use that symbol, those symbols. And they do it in another way with something called logarithms, but it's exactly the same thing. We just have to understand the relationship between this number, and this result. And that's exactly what happens when you're doing, when you're using these radical signs. Okay, so I know that for some people that's a little bit simple, and I hope to get to something that you will also consider not so simple at all, but we'll just consider some of these special relationships that numbers have with each other. And once again, in this algebra that I'm going to show you, well, in algebra, what we're trying to do is we're trying to multiply, for instance, these variables against each other, and it's all very easy when they fall in line algebraically. And what I mean by that is, let's see if I get that. All right, so this is how the universal law of numbers code is actually teaching us how the thing works, because if we are to multiply a number that has the same exponent against another number with the same exponent, well, we can do that, and it's no problem, because, for instance, 2 to the third times 4 to the third, 2 times 4 is 8 to the third. And also, if we have the same coefficient, this number here, it's always easy because, for instance, 2 to the 7th times 2 to the third is 2 to the 7 plus 3. And that's 2 to the 10th. And that makes it very easy. But what you can't do in algebra is go 5 to the third times 6 to the fourth. That's not 30 to the 7th. That's not the way it works. So what this universal law of numbers code is actually doing is it's teaching us how the thing works and how you get the correct answer. So anyway, so we have special relationships between numbers, and we know that. We have the even numbers and the odd numbers, and that's all well and good. And we have 3, 6, and 9, and that's understood. But basically, I will show you a relationship that the 2, 4, 8, 7, 5, 1 numbers, or 1, 2, 4, for instance, and 8 have against or with 5, because if we take 1 and half it, and keep on going, or 2 and half of it and keep on going, it's the same as 1 and halving it, because the first one, divide 2 by 1, now you're at 1. If we do it with 4 or 8 for the same reason, it will always give us this code. But these codes are the same code as when we multiply the number 5. 5 times 5 is 25, times 5 is 125, times 5 is 625, times 5 is 3125, times 5 is 15,625, and times 5 is 78,125. So we can see that there's a relationship there between 1, 2, 4, 8 and the number 5. And this is important because basically the issue at hand is we can do amazing arithmetic. We can multiply, for instance, and calculate amazingly huge numbers using this very easy form. However, we just have to understand what the rules are and how they exist. Now, any of the rules that come with the universal law of numbers, they're all given by the system. You don't need to read a rule book, and nobody has to teach you any rules. What you do is make calculations with the universal law of numbers, and you will quickly see if you're getting the right number or the wrong number, and you will always know. You just have to check it. Okay, so here's another way we can look at that. Now, if we do it with denominator and the numerator, do it like that, the same thing happens. It still gives us 5, 25, 125, 625, 31, 25, 15, 625. And it also still gives us what I call the 248751 code, because this would be 248751, and so would the others. Okay? All right, so as far as these important numbers go, 2 and 4 and 8 obviously are very important numbers, and they're very, very important, especially in the lower numbers, because we work with them. But if you think about it, numbers can get far larger than that. And on the next level, the numbers that are important are 16, 64, 256, 1024, 4096. It's just doubling as the numbers get larger, and we see that's a 2 to the something, and it's also a 4 and an 8 and a 16 and a 32, etc. to the something. And there's a sequence: 4, 6, 8, 10, 12, 14, 4, 8, 16, 32, 64, 128, doubling, 2, 3, 4, 5, 6, 7. So what we're doing is we're recognizing this sequence. And by recognizing the sequence, then when we look at the thing overall, it will all seem much simpler to manage somehow. Now, another trick with the numbers is we can get from 2, 4, 8, 7, 5, 1 numbers, which is what these are. Now watch when we reduce. 2, 4, 8, 1 and 6 is 7, 32 is 5, 6 and 4 is 1. That's why they're 2, 4, 8, 7, 5, 1 numbers. We're going to, if we multiply them by any, 5 or any number divisible by 5, we're going to come up with a number that has 0 at the end. And that's another big help because we work in increments of oftentimes from 10 to 100 and 100 to 1,000, etc., etc., etc. So if there's a way to get the number to a 0, well, I'll show you an example of how we will be able to do that. And it's by multiplying them, let's say 2 times 4 times 5. Okay, so now what we'll do is we'll just briefly explore how algebra comes about through the universal law of numbers. And basically, it's like skimming through the pages of the textbook and knowing that these all exist and that one can do them at their own leisure. Because all you have to do is write out the universal law of numbers code and make it into numbers, and you will come up with this same matrix that I do, and you will see all of these things that exist. So let's say 2 times 5 is 10. That's a 1 with 1 0. Well, if that's true, then 4 times 25 has to be a 1 with 2 zeros. And 8 times 125 has to be a 1 with 3 zeros. And 16 times 625 also must be a 1 with 4 zeros. And 32 times 3125 will be a 1 with 5 zeros. And that's the way that's going to work. And it will go on and on and on. Okay. So we know that 5 times 6 is 30. That's a 3 with 1 0. Then 25 times 36 will be a 9 with 2 zeros. 125 and 216 will be 27 with 3 zeros, etc., etc. And you can see we're getting the sequence here. 30 squared to the 3rd to the 4th to the 5th to the 6th to the 7th. We can look at a relationship that exists between groups of numbers. For instance, in the universal law of numbers code, we see that 1 and 4 is 1 times 4 is 4. 16 times 25, that reduces to 4, it's 400. And 49 times 64, that will also reduce to 4. And that's 3200 minus 64, which is 3136. Okay, 3 and 1 is 4, and 6, 10, and 1, 3, 6, 3, 3, 6, 3, 1, 3, 6. 3 and 1 is 4, and 3 is 7, and 6 is 13, and 1 and 3 is a 4. But without getting caught up in all of that, what we're just doing is we're looking to see, I'm going to help identify that there are patterns going on here. 1 times 4 is 2, 1 times 2 is 2, so this is x squared, so 1 times 4 is 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared. 16 times 20, 400 is 20 squared. So it's going to be 20 squared, 20 to the 3rd, 20 to the 4th, 5th, 6th, 7th, 8th. 7 times 8 is 56, so this is 56 squared, 56 to the 3rd, 4th, 5th, 6th, 7th, etc. And 8th, 9th, 10th, 11th, 12th, 13th, etc. So we're identifying another pattern. And here's another simple pattern we might see. We know that 2 times 6 is 12. Well, then 4 times 36 will have to be 12 squared. 12 to the 3rd. 12 to the 4th, 5th, 6th, and 7th. That's a relationship. Here we see this relationship. 2 times 7 is 14. So 4 times 49 must be 14 squared. And it is. 14 to the 3rd, 4th, 5th, 6th, and 7th. Okay, now we'll get up to a number like this. Okay, 16 times 49, well, that's 784. Fine. Because 4 times 7 is 28, so 784 is 28 squared. And 28 squared, 28 to the third, to the fourth, to the fifth, to the sixth, to the seventh. Here it's 784. 784 squared, 784 to the third, 784 to the fourth. And that's coming out of the number 28. Okay, so just backing up and going around a little bit, just remember that it all comes from the initial 369 code matrix. Going down, 1 times 1 is 1, 2 times 4 is 8, 3 times 9, 27, 4 times 16, 64, 5 times 25, etc. And basically all that is, it's x times x squared. X times x squared in the green. Now we'll go x squared times x to the fourth. And x is 1, 2, 3, 4, 5, 6, 7, 8, or 9. So here we do it like this. X squared times x to the fourth is x to the sixth. Very good. So 2 squared times 2 to the fourth is 2 to the sixth. And that's the way that works. So here you can see it with the numbers, and you can also see it with the algebra. And it's very nice actually to know the connection, how they work, but it's very nice to know the numbers too, not just the 2 squared, 3 squared, 4 squared, whatever. It's very helpful to know what these numbers are, and the magnitude of the expansion and how large they get, yet they still always stick to this one simple diagram, the 369 code. So all of these are always the same exact thing. X squared times x to the third is x to the fifth, because x2 plus 3 is x to the fifth. And we get to know these familiar groups of numbers. And once a person begins to understand that these very familiar numbers, how they interact with each other, well, this is where the calculator actually comes in. So the 369 code is a calculator, and a very powerful, the most powerful one at that. However, it's different than the other calculators in the regard that it will teach you how to become the calculator. So if you were to explore this, and you were to study it, and you were to understand it, and you were to, become familiar with all of these numbers, then in effect, you would become your own calculator. And it happens in a incremental fashion. So here we have 8 times 16 is 128. 343 times 2401 is 823, 543, because 7 to the third times 7 to the fourth equals 7 to the seventh. So now we're just going to show that x to the 1 times x to the 6 is x to the seventh. And you can see it with the numbers. And you see how all of these numbers go. 5 times 5 is 25 times 5, 125 times 5, 625 times 5, 3125 times 5, 15625 times 5, 78125. And it goes backwards in the same fashion. So now we're going to look at this connection. So 25 times 64, that's going to give us 16 with 2 zeros. That's going to give us 1600. So 125 times 512 will give us 64 with 3 zeros. And 4096 times 625 will give us 256 with 4 zeros, etc. And 2 times 4 is 8, so 4 times 16 must be 8 squared, and it is, it's 64. And 2 times 4 times 8 is, 64. So 4 times 16 is 64, times 64 is 64 squared. 8 times 64 is 512, so 8 times 64 times 512 is 512 squared. And we'll just do 3 to the 6th times 9 squared times 9 to the 6th. And what we're going to get is here I'm just showing you how we can make the transition to get from a 3 to the 6th, and now we want to make it 9. Well, 3 to the 6th is the same as 9 to the 3rd. And if we understand that, then we know that we can make it 9 to the 3rd times 9 to the 8th, and we add 3 and 8, and we have 9 to the 11th, because we can't just go 3 times 9, 3 to the 6th times 9 to the 8th. You'd have to do those numbers out first. You can't add these exponents together or multiply like that. So once again, that's how the 369 code is teaching us what you can and you cannot do, and you begin to understand what the structure is. And we have 2 squared, and here we have 4 to the 7th, and we can get a 2 squared to make it into a 4. 2s are easy to get to 4s. 2s are used to get to 4s, to get to 8s, to get to 16s, to get to 32s, to get to 64s, etc., etc., etc. Here we're just showing how we're going to do this 3 times a 5 and an 8. So we have a 3 times a 5 and an 8. But that's how we can get to these round numbers. 3 times 5 times 8. That's going to give us 120 to the 3rd. Now, 2 squared times 2 to the 7th to get it to be 8 to the 3rd. Well, 2 squared times 2 to the 7th is 2 to the 9th. That's 2 to the 3rd times 2 to the 6th is also 2 to the 9th. And we know that 2 to the 3rd is 8. So we can do it like that and get 8 to the 3rd. But if the whole point is everybody can do it however they like, as long as they obey by the rules. And I'm aware that different people do it different ways, but what I'm showing you here is in this universal law of numbers, since all of these numbers are pure numbers and constituents of the pure numbers, we can always find ways of multiplying them and combining them against each other to get these pure results that are given in the universal law of numbers, because it's a perfectly symmetrical universe that it has. So we have 4 times 9 is 36. So 16 times 81, 36 squared, and then 216 squared, it's okay, so this is how you keep it squared, because 6 times 6 is 36, times 6 is 216, times 6 is 1296. So it's just 36 squared, 216 squared, 1296 squared, 777 6 squared comes from 4 times 9. You see how we're getting that? Okay, that's one like that. Please stay up a little bit, cooperate today. And now we're just moving on. And I hope I'm not moving too fast and I'm not moving too slow. But we see what happens when we get a 3 against a 9. Well, we can do that. 3's go against 9's because we know that 9 is divisible by 3, so it's easy to get into something there. 9 times 81 is 729, and likewise 81 times 6561 will be 5,000.